So in this lesson we will look at expendable mold processes. This means that the mold is expended after every casting, and which means that for every casting or every bunch of castings we need to create a separate mold. Now this includes essentially what I call as sand mold processes, but also shell mold, investment mold, and so on. So in this lesson we will look at a typical sand casting foundry. How does it look like, what are the activities in that, the flow chart of that, and little later we will look at different types of molds, and at the end we will look at a bit on process parameters of sand casting. To start with, when you say expendable mold processes, it can be either the mold is expendable anyway, but the pattern also could be either expendable or permanent. Okay. And within permanent pattern but expendable mold processes, we typically have green sand, which is the king of all casting processes, but we also have increasingly use of what is called as CO2 or dry mold. We also have no bake mold, various molds made by combining different kinds of resins. You can have what's called as cold box and hot box, and many other industrial casting processes. But green sand to this day takes the cake because it is essentially highly economical. Now on the expendable pattern side, what we have is, what we do is we need a separate pattern to also make every mold or every bunch of molds. Okay. In this case again we have two major processes. One is called the investment mold, where we use a wax pattern, or you may have a what's called lost foam process, where you use a polyurethane foam. Now as we see a little later, within lost foam also we have what's called as a where we keep the foam in the mold and metal burns the foam through and then flows, or you may burn out the foam before you make the casting or pour the mold. Now on the permanent mold side, which is metal mold side, again the major process there is die casting, and within die casting, depending on the pressure involved in flow, you may have either a gravity die casting where metal is flowing under gravity, or low pressure or high pressure die casting. Within high pressure we again talk about hot chamber and cold chamber. Hot chamber is where the metal is melted near the die itself, and in cold chamber where you melt the metal separately and pour it into the die. Again obviously because of this reason, in cold chamber we can make higher temperature castings like copper base alloys, whereas in a hot chamber machine, because you are melting there itself and you can't melt very high temperature metals in the die itself, otherwise die life will go off, we are talking about aluminum base alloys. Now other kinds of die castings are centrifugal castings, where you can say most of them are metal molds, so that's why we put them in permanent mold here. Again you can have centrifugal casting, where we can create a hollow cylinder without putting a core, or we have semi-centrifugal or centrifuging casting, where we are putting a number of castings in around a central axis, and we are rotating the entire mold, so metal is flowing into the castings under centrifugal pressure. So it's a different way of letting the metal flow into the casting. And then we have a few special processes which are still not come full-fledged into industry, but they have highly promising characteristics, which include semi-solid processes, and continuous casting is used in industry to create billets and blocks, but semi-solid casting is where we are talking about the boundary line between casting and forging. In forging you are not melting the metal, it's only heating the metal. In casting you are completely melting the metal. In semi-solid we are using the characteristics of between the mushy state, you are trying to pour the casting, and it creates its own special properties and characteristics. Now sand casting, if you can look at all the terminology, a typical sand mold may comprise of not only the top half, which is called as a cope, and the bottom half called as a drag. You need to make it in two halves because you need to create the cavity first using a pattern, and then you have to remove the pattern before you pour the mold. So to be able to remove the pattern from the mold is made in two halves called cope and drag. Now you also can put a core in the middle to create a hollow shape, in this case a side blind hole, okay, and other elements of a casting like feeders and gating, the gating system itself comprising of sprue and runner and gates. All these things we will see later in other lessons. Okay. And then the typical flow chart in a sand casting foundry looks somewhat like this. Later on we will show you actual photographs of a typical typical foundry. On one side you have the incoming chemicals and the sand and chemicals are mixed to create the sand mix, which is used for molding. But for creating the mold we need the pattern and the core box. So these are manufactured or kept in a tool room or a what's called as a pattern shop. On the other side, you have the metal and other additives and other elements in the metal. Usually they don't melt only virgin metal. They will take some virgin metal, some scrap, and some foundry returns. Essentially, when you cut the feeders and gating, we recycle them in a foundry. So you mix all of them in the right proportions to get the right composition of the metal. Then you melt it in a induction furnace or a arc furnace or a cupola for a low cost foundry. And then usually furnaces melting and then the pouring may not be synchronized. So to reduce the cost and to melt more metal, you can also have a holding furnace or a holding ladle. So you hold the metal in a ladle and then you take it to from ladle you take it to the pouring stage. So molds come from one side, cores come from one side, you assemble the mold, cores in the mold, and then from the other side you get the liquid metal, you pour it into the pouring stage. That's the critical moment in a foundry. The event which everyone waits for is when the metal is poured into the molds. Then the molds are let to cool. The casting has to solidify and then it is left for some time to cool depending on the size. If it's a large size casting, it can take hours. A huge casting can take even days to cool. And then after it cools, you shake out the casting from the mold, essentially break the mold, break the sand mold, and then remove the casting from the mold. The sand may be sent back for recycling and much of it can be reused. And on the other side, the castings which have already gates and feeders and all that, they are taken to other side for fettling, where you essentially cut off the gates and feeders. Then a little bit of grinding and finishing, maybe some rough machining, maybe before or after inspection. Inspection itself is done in different ways, like X-rays, or it could be measurements or dye penetrant or ultrasound. And then some castings may be heat treated if necessary, and they may be painted before they are delivered. That's a typical flow chart in a foundry. The most foundries, they try and lay out so that the material movement is minimized, so in a compact area you can have high productivity. Now this is a foundry, a typical Indian foundry with a semi-automatic molding line. So you see those jolt squeeze molding machines at the back and the molds coming out from those machines in the front. These molds are ready for pouring. And this is the melting station, where you see two induction furnaces. The flames are coming out from the induction furnaces. These are where the metal is, all the raw materials and the returns and the scrap are mixed in the right proportions and melted. They take samples out to inspection to verify the composition in a spectroscopy, and you see the molding lines in the background there. The metal is taken from this, taken into a ladle, a pouring ladle, holding ladle or a pouring ladle, and once it is transferred, then it is taken to the pouring line for pouring. As you can see, it's sometimes interesting to actually watch in a foundry and use your stopwatch to see how much is the pouring time. And many times you find that the pouring time of the first casting to second to third casting, the variation can be as high as 20-30%. That is what we can measure by stopwatch. What we can't measure is the pouring temperature. But it's very easy to visualize that the first casting is definitely will have much higher temperature than the last casting in a line. Okay? And that variation is one of the many parameters in a foundry which are difficult to control. Obviously you cannot tap a ladle for every mold at the right temperature. You have to tap it one shot and then pour it. So that variation is what leads to the inconsistent quality in castings, which is unavoidable. If you want casting at that cost, we have to accept some degree of variability of quality. Now after castings are cooled and then they are ready, they are shaken out, and here is where you see the fettling station. So these castings, many of these are still in a bunch, they still are connected with risers and gates, and these are cut off at this stage. And this is usually the most difficult, the most noisy, and the most difficult job in a foundry. And many foundries actually don't even do it themselves anymore. They outsource this part of the activity to contract laborers or some other agencies, because no one is usually willing to do this work. Increasingly, some foundries are trying to automate this. So we are trying to fettle automatically and cut off the gates and feeders. But there is some risk that casting will break instead of the riser breaking. So you have to worry about fettling being done. So manually is still the safest way of getting the right way of doing it. Now we will look at another process, which is shell molding process. Now in sand casting, we make the mold around the part can be very thick. In fact, if you are pouring 1 kg of casting, the weight of sand around that 1 kg casting can be as high as 4 to 5 to 8 kgs, maybe even 10 kgs in some cases. Now that is a lot of sand, okay, being used for just one casting. Now the one way to reduce that is to create only a thin shell around the casting instead of a thick mold around that. How do you do that? In this case, you use a metal pattern. What you see, the pattern on the top, and then there are the actual the shape which you want to create is at the below the pattern there. The pattern is heated, and the sand is usually a little more finer sand than green sand casting. This sand is mixed with some resins, okay, and these are essentially thermosetting resins. So when these resins come in contact with a hot pattern, they polymerize, they harden, and while hardening they bind the sand particles. Now this can be a very thin but very strong shell around the pattern. And then you strip the pattern, essentially means that you remove the pattern from this, and you are left with the shell. Now what they do is, if you see in the second picture where the metal is being poured, the actual shell is in the center around the hot metal. But around the shell, just for backing it up and giving some strength, you can pack some loose sand. This need not be molded, it can be just poured into another flask around the entire shell. So you put the shell in a flask and then pour loose sand around the shell. And this loose sand, because it doesn't come in contact with the liquid metal, can be easily and fully recycled. Only the shell recycling can be done a different way, or it can even be sacrificed. Now that's a small thickness of material there. So this is a much more, you can say, efficient process in terms of usage of mold material. You also get much better dimensional tolerances and surface finish compared to green sand casting. Now going in this direction, the next sand based or dispensable mold process is investment casting. We looked at in the first lesson how this originated several thousand years back as a lost wax casting process. This is the industrial lost wax casting process, what is referred to as investment casting process. What we do in this is, we create these wax patterns not by hand carving as we have seen earlier, but by injecting this wax in a die, just like a plastic injection molding. So we create several wax patterns, and then usually investment casting is good for small parts. So you don't want to make one part per mold, so you basically solder these wax patterns around a tree. This tree, which later on will become the gating channel in which you pour the metal, also acts like a feeding for the casting. We'll look later on what is gating and feeding, but for the moment let us say that we are stitching these wax patterns around a central sprue which looks like a tree with branches, and then the entire tree, wax tree, is dipped into a slurry, okay, and then it is coated or stuccoed with the loose sand particles. This they do it in several iterations. So you dip it in slurry, you stucco with loose sand particles, and then dry that. And again after it dries, again do one more round of dipping, stuccoing, and then drying. Like this you build up several layers of thickness, layers around the central wax patterns. And the number of layers and thickness of the layers finally depends on the part size and the part weight. The thicker the part, the heavier the part, the more layers of shells you need to give the sufficient strength. Then finally, once all the shell is made, then you heat the shell, okay, so that the wax can come out, and that wax can be recycled to some extent, although we have dimensional control problems if you use the same wax. And then before you pour the metal into the shell, you again heat the shell to very high temperature. In fact, as high temperature as the molten metal itself. Okay. Yeah. Okay. Why you heat the shell? Okay. One I mentioned just now is that you heat the shell to first of all remove any remaining wax. If you heat it to metal temperature, it can remove the wax completely. But also by heating the shell, just like a core making process, you are giving strength to the shell. The shell becomes stronger and it can withstand the molten metal flow. But even better reason than that, and that gives an additional advantage to investment casting process, is that when you heat the shell, the metal, when it's filling the cavity, mold cavity here, it can easily flow into the narrowest of sections. So if you want to make, let us say, 1 millimeter wall thin casting, It is not even possible by pressure die casting. With all the pressure in the die is made up of metal or steel, which has a very high heat transfer rate. So before the metal even can fill the die completely, it will freeze. Whereas in this case, you can actually go at 1 millimeter and even below 1 millimeter wall thickness, because the shell is hot and it keeps the metal flowing. Okay, that's a big advantage of investment casting. So even today, investment casting, although it is the oldest process, it is still the most valuable process, because you can make very intricate parts, very thin wall parts, okay, with very high dimensional tolerance and surface finish. Okay, and finally, when you pour the metal and the metal cools down, after it is done, you break the shell and then you get the casting. You fettle the individual castings and then go and finish. Usually many of these investment cast parts can be just done basic finishing, basic machining or finish machining, and they can be used. They don't have to machine too much. So it is what is called as a near net shape process. What we get is very close to the original design part. Okay, and here is an actual investment casting foundry. This is called as unidirectant foundry, which is in Thane near Mumbai itself. And this foundry, you can see the first station, you can see that wax patterns are being injected in an injection mold. Okay, and then you're taking the big sprue, like a cup, what you see in the picture here, and it's like impeller. What you're seeing this woman doing is she is gluing the impellers around the sprue, and then you are seeing in the third picture they are dipping that in the ceramic slurry and getting a coating of that. And in the next picture, which you see, is stuccoing with the loose sand, shower of loose sand particles, and after doing that, you dry it in an air conditioned room. These shells are dried in an air conditioned room, and that gives it the required strength. And finally, you heat the shell as we just discussed, and then you pour the metal into the shell. That's the basic investment casting foundry. Okay, to summarize, what we have learned in this lesson is that there are a variety of casting processes within which we are talking about either permanent mold processes or dispensable mold processes. In this lesson, we focus on dispensable mold processes, which itself can be made using either a dispensable pattern or a permanent pattern. The last one which we have seen was dispensable pattern, dispensable mold process, which is investment casting. The first one which we have seen was a permanent pattern and a dispensable mold process, which is a green sand mold process. Okay, and then we looked at the various steps in a typical sand casting foundry, starting from mold making and core making to melting, pouring, fettling, and finally shipping that. What we want to emphasize here is even this basic overview of casting process would have given you a clue that there are a large number of parameters, material parameters, not only cast metal but also the mold material parameters, core material parameters, and other elements which are used in a mold, which we'll see later, plus your process parameters, all melting, pouring, molding, all those parameters, and finally your end processes like your heat treatment and inspection and so on. So all these parameters together have a cumulative and all kinds of interesting interrelationship between parameters leads to cumulative effect on cost and quality and productivity, how many castings you can produce per day, and that is not easy to gain mastery of. So casting is for the brave, it's not easy for everyone to do this. So we'll stop here.